Hey, this is lecture number 8, which is my crash course in polyhedral combinatorics. So let's see what we're going to do here. It's really the basics in polyhedral combinatorics which are necessary in a course, I think, in discrete optimization. And a large part of the lecture is going to be about some of the fundamentals for polyhedra and polytopes. Okay, so that's going to be very geometric. Later on, we will define total unimodularity as a concept or a condition under which linear programs always have integer optimal solutions. So we talk about integrality of solutions to linear programs. And then at the end, we move towards so-called Schwatter-Gomery cuts, which is actually a description of any integer program by means of linear inequalities. Okay, so as a motivation to study all that, remember the minimum cost flow problem that we had in the last lecture. And as a matter of fact, by the algorithm that we constructed, which was the primal dual algorithm, we have seen that we always obtained an integer optimal solution. So a minimum cost flow in the network, which only sends integer amounts along the edges. Of course, given that all the input data is integer, right? So that means all the capacities, the balances, the upper capacities, and the costs, that is assumed to be all integers. And then we have seen by means of this algorithm that there was always an integer optimal solution. Okay, so more generally speaking, we have seen a certain class of linear programs and also the dual of that linear program, which always had integer optimal solutions. And well, that is of course not a coincidence. And in particular, that is not true in general. So if you give me an arbitrary linear program, it need not have integer optimal solutions, even though all the input data, all the parameters are integers. And a very simple example is this one here. So we have a linear program here with all input data integer, even all input data is 0 or 1. And the problem is a matching problem on a triangle. So if you look at the picture here on the right, we want to compute a matching in this simple graph, which is just a triangle. So that means we are selecting edges 1 or 2 or 3, and you already see that we can only select one of the edges because it's required to be a matching. And what's the corresponding linear program? We want to compute a maximum matching in this graph. So we maximize the number of edges that we select. So xi would correspond to the decision to select edge number I. And what is the constraint? Well, the first constraint says that x1 plus x2 can be at most 1, which corresponds to the constraint that for this vertex here, we can only select one of the incident edges. And the same for this vertex and this vertex. So therefore, we got the other two inequalities here. So that's a linear programming problem. Quite simple one. All the input data, all the coefficients in the objective function and in the matrix and on the right-hand side are integer numbers, just zeros or ones. Nevertheless, the optimal solution to this linear programming problem is just a vector 1/2, 1/2, 1/2, right? So if I set all the values x1, x2, x3 to 1/2, I get an objective function value of 3/2, and I fulfill all the constraints because that would be for this vertex 1/2 plus 1/2 is 1, which is feasible, and the same here and here. Okay, so this is a very simple example to show that even though all the input data is integer, the optimal solution is only obtained for non-integer solution values. So the question is, under which conditions do we get integer optimal solutions? So apparently for this problem, this is not the case. And also studying the question, well, what is the difference or what is the gap between, say, the linear optimal solution, which includes fractional solutions, and integer optimal solutions, which in this case would be selecting only one of the edges and only gets us a value of 1 as opposed to this 3/2 here. And in order to study these problems, we are going to look at the object where such a linear program actually lives. Okay, so that is an object which is defined by a set of linear inequalities, and that's a polyhedron or a polytope. Okay, so we need the definition of a polyhedron and a polytope. So a subset P, subset of Rn, is a polyhedron if it's just a solution of a finite number of linear inequalities. Okay, so that's just a description, the feasibility description of some optimization problem, say. So that's all the vectors x and Rn which fulfill a set of linear inequalities. And each of these linear inequalities corresponds to or defines a half space, right? So a linear inequality would give me, in R2, would give me a line. And this smaller or equal means that all the solutions have to lie below this line. Okay, so for example, here in this linear system consisting of 3 linear inequalities, the first inequality would correspond to this line here. The second one would correspond to this line here, and the third row or inequality would correspond to this line. And so we get as a feasibility region for such a linear program which has these feasibility constraints here, we would get this region here. That would be all the feasible solutions to this linear system. So that's just the definition of a polyhedron, the intersection of finitely many half spaces. Okay? And a polytope is the same, only it's required to be bounded. So notice that in the polyhedron up here, that contains such an infinite ray. So we can move into this direction indefinitely. And down here, I have changed the last inequality to something else. So I've changed the coefficients here and the right-hand side here to get this inequality. So the third inequality means I have to be in this upper region here, right? And as a result, I get a bounded polyhedron, and such a thing we call a polytope. An alternative definition for a polytope would be it's a polyhedron which fits into some box. Okay. Now, once in a while, we will also be talking about the dimension of such objects, so the dimension of polyhedra or polytopes. And if you look at these two figures, it should be intuitively clear that these two objects would have dimension 2. So that's 2-dimensional objects, right? I mean, it's like flat objects, which kind of correspond to some subset of a hyperplane. A 1-dimensional object in R2, that would be a singleton line, and a 0-dimensional object would be a single point, for instance. To be a bit more formal on the dimension of a polytope or a polyhedron, we need to define what it means to be affinely independent. So given a set of vectors, x1 up to xk in Rn, we say that these vectors are affinely independent intuitively if none of the vectors xi can be obtained as a linear combination of the others. Okay, so formally that means if I sum up a linear combination of all the vectors x1 up to xk with certain parameters lambda I, with the property that the sum of these lambda i's is equal to 0, then the only solution to these equations is that all the lambdas should be equal to 0. So affine independence is just like linear independence, with the only exception that we also require that the sum of the lambdas should be equal to 0. And it can be thought of as the coordinate-free version of linear independence. The best intuition really is that we call vectors affinely independent if none of them can be expressed as a linear combination of the others. So let's look at a small example here in R2. So here we have two vectors, two arbitrary vectors x and y in R2, and let's just write down what the conditions require. So if I have that the sum, so lambda 1 x plus lambda 2 y is equal to 0 and lambda 1 plus lambda 2 is equal to 0, then affine dependence requires that the only solution to this system is the trivial solution where the lambdas are equal to 0. So obviously here lambda 2 is minus lambda 1, so we obtain that lambda 2 y minus x is equal to 0, and this actually means because we have two different vectors x and y, and coordinate wise this should be equal to 0. So that means that because x is not the same as y, we immediately get that lambda 2 is equal to 0, and hence also lambda 1 is equal to 0. So that means I actually took two arbitrary vectors x and y in R2, and they are affinely independent. As a matter of fact, any two vectors x and y, if they are not equal, span this one-dimensional subspace here. So this line, which is uniquely defined by these 2 points. So the line that goes through these 2 points. So in summary, two vectors x and y are affinely independent if and only if they are not equal, and they actually span this one-dimensional, even though I didn't yet define what one-dimensional really means, subspace. If I now add a third point to the set of points x and y, it would be affinely independent if and only if it's not lying on this line which is spanned by x and y. So if I would add a third point h here, that would be affinely independent, and the 3 points together would indeed span a two-dimensional subspace, right? So how do I define the dimension of a polytope now? Well, I just take the number of affinely independent vectors, and by convention I subtract 1. So this is the definition. The dimension of a polytope or polyhedron is the number of affinely independent vectors that it contains minus 1. So here is a little example. We have a polytope P here, and I look at several subsets of that. So for example, this vertex here, V1 over 2, or this so-called face F here, and what are the dimensions of that? And I mean, intuitively, that should have dimension 0. This line here should have dimension 1, and this whole polytope here should have dimension 2, and that is exactly true. So the dimension of V1, that's just a single point, is equal to the dimension of V2, that is equal to 0. So that's the number of affinely independent vectors, that's just 1, minus 1 equals 0. So the dimension of F, for instance, so this line here contains two affinely independent vectors, but only 2, because everything lies on this line here. So therefore the dimension is what it should be. It's equal to 1. And the dimension finally of the whole polytope, which contains 3 affinely independent points, is equal to 2. So dimension of P is equal to 2. So intuitively, that should be clear. Okay, so the next definition that we're going to need is that of a supporting hyperplane for a given polyhedron or a polytope. So given is some fixed polyhedron P, and then a linear equality, so all the x that fulfill this linear equality Wx equal to T, that defines a hyperplane in Rn. So in R2, that would mean an object of one dimension less than R2, so that would be a line. And in this picture, that would be this line here. And that is when W is a non-zero vector and T is just some value, right? So Wx equal to T can also be thought as the intersection of the two opposite half spaces, and then what remains is exactly the line defined by Wx equal to T. Here in the figure, the W is the vector 3, 1. So then that would be on the right-hand side, T was chosen to be 15, and that would correspond to exactly this line here. And the vector W, of course, is orthogonal to the corresponding line. Okay, so if we look at the inequality, Wx less or equal than T, we say that such an inequality is valid for P if the polyhedron or polytope lies in the corresponding half space. Okay, so here in the figure, that would be the line. The inequality Wx less or equal than T would be this half space, and indeed the polytope lies completely in that half space. Okay, so that's a valid inequality for a polyhedron, and it's called a supporting hyperplane if it's not only valid, but also if it has a non-empty intersection with a polytope. Okay, so if I would define this line here, then it would be a valid inequality for the polytope, at least if I define the inequality in the right direction. But it would not be a supporting hyperplane, it would only be a valid hyperplane. And this one here has a non-empty intersection with the polytope, which is the singleton point here, in fact. And that is a supporting hyperplane for the polytope. Another supporting hyperplane for the polytope would be, for example, this inequality which defines the polytope. So the inequality that defines this half space would also be a supporting hyperplane for the same polytope P. Now in this picture here, the supporting hyperplane intersects with the polytope at the singleton point here, right? So the intersection of the hyperplane with the polytope is the point 4, 3. And this intersection of a supporting hyperplane with a polytope, that also deserves a name. That is what we call a face of the polytope. Okay, and that we do for any supporting hyperplane of the polytope. So the definition of a face is you give me a supporting hyperplane of the polytope, and then this intersection, which by definition is non-empty because it's a supporting hyperplane, this intersection is called a face of the polyhedron or polytope. Okay, and we have an important theorem on the characterization or the description of such faces. Okay, so the faces of a polyhedron really can be seen as the outer description of a given polytope. And the theorem is the following. So any face of the polytope can be described essentially by taking a subset of the defining linear system. Okay, so remember that the polytope itself was defined by taking all vectors in Rn which fulfill a system of linear inequalities, right? And now from this linear system, we take a subset of the corresponding linear inequalities and we set them to equality. Okay, so this A0 and B0 is just some subsystem of the original descriptive system of the polytope. And the theorem says that any face, or we have a face if and only if it is described by such a linear subsystem. And the second part of the theorem says that, well, even more special if we have to talk about an inclusion-wise minimal face. So in this picture, that would be actually the vertices of this polytope here. Then the linear description is exactly given by just this equality system here. And the rank of the corresponding matrix, submatrix that I choose is equal to the rank of the original descriptive system. To make that a bit more concrete on the example, so here we have the descriptive system Ax less or equal than B that describes the whole polytope P here, okay, by 3 inequalities. And the theorem says that any face, so that means this is a face of the polytope, this is a face of the polytope, This is a face of the polytope. This is a face of the polytope, and so on. Any such face can be described by a linear subsystem of these three inequalities here. And you see, for instance, a subsystem here in red. So that's the third and the first inequality. And if I choose this inequality and this inequality, and I set them to equality here, I get this equality system. And that is exactly the intersection of these two lines here, which gives me that face of the polytope, this singleton point here, at the vertex of the polytope. If you look at another example, so for instance, how do I get this face here of the polytope? That would be the corresponding inequality, just the first one. And if I just pick the first inequality, that would define me the whole line, and the intersection with the polytope would give me the face. So that's such a description of the corresponding face here. So any face can be obtained by taking some subsystem. It could, by the way, also be the empty subsystem. When I choose nothing here, then I just get the polytope itself, which is also a face of the polytope. So an arbitrary face I get by taking an arbitrary linear subsystem, and a minimal face, inclusion-wise minimal face, I get by taking a maximal subsystem, maximal in the sense that I take a maximal number of linear independent rows of the matrix. So here in the example in R2, taking a maximal number of linearly independent rows, that will always be 2 rows of the inequality system, which will actually define the vertices or the corner points of this polyhedron, right? I mean, that will be the intersection of these two lines, and these two lines. So that would be the maximal linear independent subsystems, which define the minimal faces of the polytope. So this is what we want to show. Any face of a polyhedron, or say polytope P, can be obtained by taking a linear subsystem of the defining inequality system. So we take some rows and right-hand sides from this linear system AX less or equal than B, and we set those to equality. And this gives me a description of the face of the polyhedron. That is true for any such subsystem. So this is an equivalence. Let's first look at the direction from left to right. So we start out with an arbitrary face of the, say, polytope P, okay, and say this face is obtained as the intersection of P with this hyperplane Wx equal to T. So since this was supposed to be a valid inequality for the polytope, all the points from the polytope fulfill Wx less or equal than T. And at the face, we have equality. So this face is exactly all the optimum solutions for this of this linear programming problem. We maximize this objective function W times X subject to the constraint that the point lies in the polyhedron P. Okay, so at the optimum solutions, the optimum solution values will be equal to T, because for all the points from the polytope I have smaller or equal than T. And at the face, I obtain equality. Now, since I talk about optimum solutions to a linear programming problem, there exists a matching dual optimal solution, right? So that means for all points x in this face F, so for all these optimum solutions, there exists a dual solution, let's call it Y, and that is going to be a solution of the corresponding dual problem, which is minimize y times b subject to the constraint that y times a is equal to w and y should be non-negative. Why do I have equality here? Well, that's because in the original problem, the variables x are unconstrained in sign. They are not required to be non-negative. Okay, so that is a dual solution, but a dual optimal solution has to fulfill complementary slackness. So that means with yi strictly larger than 0, implying that the corresponding primal constraint is fulfilled with equality. So ax at position I is equal to bi. And as I said, this is complementary slackness. Now I do the following. I pick any such fixed dual optimal solution. Okay, so I take any such y here, and I use this y to define my linear subsystem. Okay, so I do the following. I define A0 and B0 to be the rows of the linear system A, B, where the y's are non-zero. So with yi strictly larger than 0 for some fixed optimal dual solution y. So for some fixed y. And now let us just write down what I know about the corresponding primal solutions. So that means that for all x in P that fulfill this subsystem, this chosen subsystem with equality, so with A0x being equal to B0, we know the following. We know that the objective function value wx is equal to, that's the dual constraints, y times a times x. And now I claim that this is equal to y times b. Why is that? Well, because whenever yi was strictly larger than 0, we know that the corresponding primal constraint is fulfilled with equality, right? So ax I is equal to bi. And therefore, I get this equality here because for all the y's which are 0, I have a 0 on both sides, and for all the y's which are strictly positive, I have equality here. But now notice what we have written down. So for all x from the polytope which fulfill this subsystem with equality, I get that wx is equal to y times b, so that's a primal optimal solution. And the primal optimal solutions that were precisely elements from F by definition of F. So that means we can conclude that all the points from the polytope fulfilling this system, the subsystem with equality here, it's a subset of these optimal solutions. And I also claim that the other inclusion is true. So also we have that for all x in F, this subsystem must be fulfilled with equality. For assume this would not be the case, so let's assume that there would be some index where this is not true. So AXI is strictly smaller than BI for some index I from the chosen indices. Okay, and then we would get that W times X by the dual constraint is equal to Y times A times X. And now I claim that this would then be smaller than Y times B, which is equal to T, which contradicts our assumption that X was an optimal solution. And why do I have this strict inequality here? Well, because we know X is a feasible point from the polytope, so it anyhow fulfills AX less or equal than B. And we just assume that AX at index I would be strictly less than BI, and the corresponding YI is also strictly positive. So therefore we would get this strict inequality here. So in total, we can conclude indeed that all the points from the polytope fulfilling this linear subsystem equal B0, that is precisely our face F. Let's also look at the other direction of that proof. So if I take an arbitrary subsystem of the linear system, so A0x equal to B0, okay, and I define F to be all the points from the polytope that fulfill this subsystem with equality, this also gives me a face of the corresponding polytope. So let's consider such a set F, and I have to identify the description of the corresponding face of the polytope. And I do that by the following trick. So I have selected some rows of the original matrix A here, and now I just take the vector W, the row vector W, as the sum of all the rows that I selected from the matrix. And the right-hand side T is going to be the sum of all the BIs, all the right-hand sides that I selected. And I claim that my set F, defined in this way, that is precisely the set that I get when I take all the points from the polytope fulfilling this corresponding equality here, Wx equal to T, and that is exactly the description of a face of the polytope, right? So why is that true? Well, because being a point of the polytope P means that AX is less or equal than B. And now, in essence, this equality here, Wx equal to T, means that aggregate, or for all these inequalities that I selected, I will have equality, but only in sum, so only in aggregation. But since all of them are fulfilled with inequality anyhow, this also means that they will be fulfilled individually. So let me write down what I mean precisely. So if I write down Wx, by definition of the W, that's the sum of all the selected rows. So that is AI, the ith row of the matrix, times X. And that is now equal, so that's our aggregate equality here. So that is now equal to T, which is equal to the sum of the corresponding BIs, right? Well, and now since this equality holds in aggregation, so in sum, and because I know that AIX is smaller or equal than BI for all indices, actually for all I, right? Because we are still talking about a point from the polytope which fulfills all the defining inequalities. That implies that if they are fulfilled in aggregation, that then I must have equality everywhere, right? So AIX is equal to BI for all selected indices I. And that's precisely what I needed to show, because that shows that whenever I select a linear subsystem fulfilled with equality, then indeed I get a corresponding, I get a face of the polytope which is described in this way. So that finishes the proof of this little and innocent if and only if here. So faces of the polyhedron are precisely described by linear subsystems. But there is even more in this theorem, so there is more in this claim. So here we have described faces of the polyhedron as the intersection of the polyhedron with these linear subsystems fulfilled with equality. And that, for example, could mean that if I take the first inequality here, so minus 1 x1 plus 2x2 smaller or equal than 2, that would correspond to this inequality here. And so if I just take this subsystem, okay, so the first row here, then that would describe me this line here, and then the intersection with the polyhedron exactly would give me this face here. So I need to intersect with the polyhedron. But the second claim in this theorem is that if I talk about minimal faces by inclusion, so like this one, this would be a minimal face, it's a vertex, then I don't need to intersect with the polyhedron. So then such faces, so inclusion minimal faces, are precisely characterized by linear subsystems, and I don't have to intersect with the polyhedron itself. So this is what we still want to show. For inclusion minimal faces of a polytope or polyhedron, we have that these two sets are the same. So these are points from the polytope which fulfill a subsystem with equality, and these are points in Rn which fulfill the subsystem with equality. So the claim is that the intersection with the polytope is no longer necessary, and the whole face is already precisely defined by thus this subsystem of the defining system Ax less or equal to b. Now, obviously, by definition, we have inclusion in one direction. Okay, so we have obviously that we have inclusion in this direction, so let us assume that this would be a strict inclusion and hopefully get a contradiction. So assuming strict containment would mean that there exists a vector x which fulfills all these inequalities with equality, so a0x is equal to b0, but it's not in the polytope here, so it's a vector in this set here which is not in the polytope, so that means it violates at least one of the defining inequalities. So we have that axi is strictly larger than bi for some I which is obviously not part of the selected rows of the matrix. But then I can add this equality system, so axi equal to bi. I can add that to the system that I already selected, right? And that would give me an augmented system. Gives me some system, say A prime, B prime, now with one row more and one right-hand side element more. And that defines a face, say F prime. And by definition, because now we are fulfilling this inequality here with equality, so there is going to be a face which is a strict subset of the face F that we started with. But we just assumed here in the beginning that we have an inclusion minimal face. So such a face which is strictly contained in F shouldn't exist, and that's a contradiction. And by the same argument, we also see that the rank of the selected subsystem, so the rank of the submatrix A0 must be equal to the rank of the matrix itself, because otherwise we again still could add one more row and obtain a strict subset, which cannot be. Now that we have described all the faces of a polyhedron, there is two classes of faces which are kind of special, and that is vertices and facets. So inclusion-wise, minimal faces of a polyhedron are called vertices, and I think I called them already vertices a couple of times before. And inclusion-wise, maximal faces of a polyhedron, which are not equal to the polyhedron itself, are called facets. Okay, so these two play a very important role in understanding and talking about polyhedra in general and in understanding their descriptions. So here's a little picture with a two-dimensional polytope, and then this inclusion-wise minimal face is called a vertex, and this inclusion-wise maximal face, which in this case is a part of this line here, is called a facet. And as you can see, the facets are kind of the outer description of the polytope, but also the vertices kind of correspond to the outer description of the polytope, and we will come back to that in a minute. Now, vertices, as a matter of fact, also have another characterization, which is given in this theorem here. So a point X in the polytope is a vertex if and only if it cannot be written as convex combination of two other points from the polyhedron. So in that sense, vertices are really the corner points of a polyhedron. And for the formal proof, I refer to the lecture notes, but intuitively, I think that makes perfect sense. So if we are considering a vertex here of the of an arbitrary polyhedron, and we try to express this vertex as a convex combination of two other points, then whatever one of the points is lying inside the polyhedron here, right? So this would be the polyhedron. Then in order to get this middle point as a convex combination of two other points, if this point is inside the polyhedron, the other point should be outside the polyhedron. So to get V as a convex combination of two other points, one of the points must lie outside of the polyhedron. So that's that intuition is correct and can be formally proved. And in that sense, vertices are really playing a kind of special role among all the points inside the polyhedron, because these are the only points with these properties, or with this property. Now, okay, so final remark. In general, a polyhedron need not have any vertices. To consider one example, we can define a polyhedron by just restricting, in R2, by just restricting x2 to be non-negative, and then our polyhedron would be this half space here, and as you can see, it doesn't contain any vertices at all. Okay, let me try to summarize everything that we did so far. So consider an arbitrary polyhedron, non-empty, and then of course the rank of the defining system, the rank of the matrix A, that's the number of linearly independent rows of this matrix A, which can be at most n, because we are living in Rn here. So with a rank k, then we describe minimal phases of this polyhedron by taking a maximum number, so k linearly independent rows of the matrix A. So the corresponding minimal phases are defined by taking maximum number of linearly independent rows of the matrix. And a polyhedron has a vertex, and we say it is pointed if and only if the rank of the matrix is n. So a vertex is defined by n linearly independent rows of the matrix A. Right? Intuitively, if I live in Rn, in order to get a singleton point by means of linear inequalities, I have to intersect n linearly independent hyperplanes with each other in order to get a singleton point, in order to get an object of dimension 0. Now, a final important proposition here, and that is if I have a pointed polyhedron, then any face of that polyhedron already contains a vertex. So a pointed polyhedron means the polyhedron has a vertex, contains a vertex, and then the claim is that any face of the polyhedron already contains a vertex. And that's an important proposition, which I'm going to prove next. So once more, if we have a pointed polyhedron, a polyhedron containing a vertex, then already any face of this polyhedron also contains a vertex. And in order to prove that, we pick an arbitrary face of the polyhedron, which is defined by such an equality system. As the polyhedron was assumed to be pointed, so it contains a vertex, we know that it must have row rank n. Okay, so there is n linearly independent rows in this matrix A. And if it should be the case that our system up here doesn't have full row rank, we can just augment it. Okay, so if the rank of A0 should be equal to k smaller than n, we can add linearly independent rows of A to get linear system A prime B prime such that the rank of A prime is equal to n, and then F prime, which is obtained as all the points which fulfill this augmented system, so A prime x equal to B prime, because this is a system of rank n, this will be a vertex, and by definition this F prime is a subset of F. So indeed our arbitrary face of the polyhedron contains a subface F prime, which is actually a vertex, so it contains a vertex, and that's exactly what we wanted to prove. Now this little proposition is an important ingredient in the proof of a very important and well-known theorem by Minkowski, and this is the statement. So it's a theorem about polytopes, so bounded polyhedra, and it says that any polytope described by some linear system AX less or equal to B, so a polytope is equal to the convex hull of its own vertices. Okay, so if x1 up to xk are the vertices of this polytope, then P is exactly equal to Q, and Q is defined as the convex hull of the vertices. So what is the convex hull? The convex hull, so this conv x1 up to xk is defined as the smallest convex set containing x1 up to xk. Okay, and notice that this theorem of Minkowski gives us two different descriptions of one and the same object, a polytope. So one description is P, that's a description by linear inequalities, and that is actually, if you look at the figure, description of P by means of the corresponding facets, so the maximal faces of this polytope. And Q, that's the convex hull of the vertices, so that's the convex hull of these corner points here. That is a description of the same set by means of the minimal faces, the vertices of the polytope, right? So intuitively, this theorem makes perfect sense, but also it has a formal proof, which we can now write down. And it's about the containment of two sets in each other, right? So P is equal to Q. So one direction is simple. First of all, P, the polytope, is a convex set by definition because it's the intersection of a finite number of half spaces, okay? So P is convex and it contains its own vertices, obviously. So P is a convex set containing x1 up to xk. Q is the smallest convex set containing x1 up to xk, so therefore Q must be a subset of P, so that is clear. The other containment is a little bit less simple and is done next. So we want to show that any polytope P is contained in Q, the convex hull of its own vertices. Okay, sounds intuitive, but nevertheless it requires a proof. So let's assume this is not the case. So let's assume it's strict containment. So there exists a point in P which is not in Q, okay, not in the convex hull of the vertices. So there exists this point U, which is member of the polytope P, but not contained in the convex hull of the vertices Q. So if you look at the picture, you see the convex hull of the vertices here. That's a convex and closed set. And U is a point from the polytope P, which is outside of Q. Now, since this is a convex and closed set, we can actually separate this point U from this convex and closed set by some hyperplane. Okay, and let's say Wx equal to T is the description of this hyperplane. So in writing, that means there exists this vector W and this right-hand side T, such that all the vertices are on the left-hand side from the picture, on one side of the hyperplane. So W times xi, this xi is now the ith vertex of Q, is smaller or equal than T. But the point U is on the other side, so WU is strictly larger than T. And now what we do is we optimize in the polytope P in the direction of this vector W. Okay, so we consider the maximum of Wx, where x is in the polytope P. And so this is just an objective function value now. And this value will be attained for some points in the polytope. And let's give it a name. So let's call this T star. Okay, so T star is defined as the maximum objective function value with respect to the objective function W in the polytope P. Now we know that all maximizers of this objective function value define a face of the polyhedron. So let me write down what I mean. So if I define F to be the face of all these optimal solutions, so that's all the x from P that attain this optimum value, so with Wx being equal to T star, that is a face of the polyhedron, and it's actually also a non-empty face, right? Now, since U was assumed to be a point in the polytope, so U is in P, okay, so U is a point from the polytope, the objective function value with respect to this objective function W can be at most as large, so that means T star is larger or equal than W times U, so that would be the value obtained by the point U from the polytope, and this is the optimum objective function value with respect to the function W, right? But now we know that W times U is strictly larger than T, so this is strictly larger than T. All right, we also know that for all the vertices from the polytope, we have a smaller or equal here. Okay, so for all the vertices xi, we have Wxi is smaller or equal than T. Okay, so let me copy that. So W times xi is smaller or equal than T, which means all these vertices achieve a value at most T, right? And that is strictly smaller than T star. Okay, so that means, so that is true for all the vertices, for all I from 1 up to k. So none of the vertices can achieve a value larger than T, and T is smaller than T star. So in particular, none of the vertices obtains this optimum objective function value T star, and hence none of the vertices is contained in this phase F. Okay, so let me also write that down. So xi is therefore not contained in F for all I going from 1 up to k, simply because the value is smaller than T and the optimum value is strictly larger than T. Now, okay, but that means we have obtained the following contradiction. That means F, which is a face of a pointed polyhedron, it's a polytope, and this face doesn't contain any of the vertices. Okay, so it contains no vertex, because x1 up to xk, that was the list of all the vertices of P. So that contains no vertex of P, and that's a contradiction because we had an earlier theorem or observation saying that any face will contain a vertex. So that's the end of our proof. Huh? All right, so that ends the proof of Minkowski's theorem. Any polytope can equivalently be described by the convex hull of its vertices. And now let's move slowly back to the original motivation. So why did we study polytopes and polyhedra at all? Well, because polytopes are associated to linear programs, to optimization problems, right? So polytopes or polyhedra, that is the feasible solutions to some optimization problem. So in this case, this linear program was the matching problem on a very simple graph on a triangle described by three inequalities, which were the degree constraints for the vertices of the graph and the non-negativity constraints. So the object where all the feasible solutions live for this optimization problem, that is a polytope, right? So this case, this polytope is described by 6 inequalities, which actually define facets, all of them. And these 6 inequalities are 1, 2, 3, the degree constraints, and the 3 non-negativity constraints, x1, x2, x3, larger or equal than 0. So the corresponding facets, so one of the facets, for example, would be this one here. There is another facet here, that's a facet defined by one of the degree constraints. There is another facet, which is this one here, also defined by a degree constraint, and so on. And this same polytope is described by its 5 vertices, which are 1, 2, 3, 4, 5, 3 of which actually, so 4 of which define feasible matchings in the graph, right? So that would be selecting none of the edges, that would be selecting one of the edges, another edge, and a third edge. But we also have this vertex here at the point 1/2, 1/2, 1/2. So that's a non-integral vertex. Okay, so the observation is that the above polyhedron with this inequality system or linear system here has actually non-integer vertices, even though all the coefficients have been integer. And so the next topic is total unimodularity, which excludes that non-integral vertices appear as vertices of this feasibility system. Okay, so the question that we are going to answer now is the following. What are conditions on the constraint matrix A and the right-hand side B such that all vertices of the corresponding polyhedron here are integer vertices? And the polyhedron is just a polyhedron defined by an inequality system AX less or equal than B and X non-negative, because very often in optimization, the solutions by default should be non-negative. And the answer is going to be, this happens to be the case when this matrix is totally unimodular and the right-hand side has to be integer. So why is this interesting? Well, that is interesting because of the following. So if it's really true that all the vertices of this object are integer vertices, then we can set up a linear programming problem. So for any linear objective function, say maximize c times x, subject to my linear constraints here, ax less or equal than b and x non-negative, this linear programming problem will have an integer optimal solution. Okay, so why is that? Well, because we know that the set of optimal solutions of an LP, that's a face of the corresponding polyhedron. And we know that each face contains a vertex. And we know if this matrix fulfills this property, total unimodularity, that all the vertices are integer vertices. So why do I know that each face has a vertex? That is an exercise. So one can show that any polyhedron with non-negativity constraints is pointed, okay? And that is nice, that is interesting, because that means essentially that we get integrality for free without explicitly having to require it in the definition of the problem. So we do not have to explicitly enforce this x to be integer valued. We know by the structure of the constraint matrix here, integral optimal solutions actually exist. So we can solve integer linear programming problems by an algorithm for just linear programming, which is, for example, a simplex algorithm, a very efficient algorithm. And we can do that because we know that optimal solutions, if they exist, occur at some vertex, and the vertices are all integer valued. Okay, so we get integer solutions for free without explicitly having to ask for it. And I specifically mentioned the simplex algorithm here because the simplex algorithm, by definition, returns a solution which is a vertex. So when we use the simplex algorithm, we really get integrality for free because the simplex algorithm returns a vertex which happens to be an integer valued vertex. Now, what is this magical property, total unimodularity? First of all, we define for a square matrix, an integer square matrix B, what is unimodular? That means that the matrix has determinant either plus or minus 1. Now, if I take an integer matrix A, not necessarily a square matrix, it's called totally unimodular, TU or TUM sometimes, if each square submatrix B of A has determinant either plus or minus 1 or 0. So what's a square submatrix? A square submatrix of A, so suppose this is matrix A, then we can just delete rows and columns. So here, for example, we delete 2 columns and 1 row, and thereby obtain a square matrix, namely this one, and the determinant of this square matrix should be plus or minus 1 or 0. That is total unimodularity. So total unimodularity has some implications on the matrix and some properties as well, which I'm not going to prove in this lecture, but you can easily verify that yourself. So first of all, if a matrix is TU, total unimodular, then the entries must be 0 or plus or minus 1. We're just considering the 1 times 1 submatrices. They also have to fulfill this property. Next, property total unimodularity is closed under adding or deleting rows or columns when this is unit vectors. So I could add arbitrarily many unit vectors as row vectors or column vectors, or I could delete them as well. And also it's closed under multiplication of rows or columns with minus 1. So I could change the signs of the values in any row or in any column. So you see total unimodularity is already quite special, but nevertheless it's useful. And here comes the main theorem. So if we have a non-singular matrix B, an integer square matrix with a determinant that is non-zero, and we consider the linear system Bx equal to B, okay, then the solution to the system, so x are the variables, then the solution is integer for any integer right-hand side B if and only if this matrix B is unimodular. So at the moment we still talk about unimodular matrices, so this is a square matrix B and the determinant should be non-zero. So unimodularity now requires that the determinant of B is plus or minus 1. So let's look at the proof. So this is about integrality of the solutions to this equality system here. And well, what is the solution to the system? Since B is a non-singular matrix, X is just the inverse of B times little b. So X is just B to the minus 1 times B. And you probably remember how the solutions to such a system can be computed. There is something called Cramer's rule that we know from linear algebra, namely the jth entry of the solution x, so xj, is just computed by taking the determinant of this matrix bj and divided by the determinant of the matrix B. And what is this bj? Well, bj is just the matrix B itself, only at the jth column I replace the jth column of the matrix B by the right-hand side B from this equality system here, okay? So this thing is the matrix Bj, and so the solution can be computed in this way. Okay, so if you haven't seen that before, you just Google Cramer's rule linear algebra, and you will probably find plenty of material about that. Now I want to argue that this x is integer valued, so these values or these fractions should be integer, but we know that the determinant of B, the denominator is plus or minus 1, and Bj is an integer matrix, so therefore its determinant will be also integer valued. So we get an integer value divided by plus or minus 1 that remains an integer value. So indeed, if B is unimodular and the right-hand side little b is integer valued, then the solution X is also integer valued. What about the other direction? Well, if we know that X, the solution X, is integer valued for any right-hand side little b here, okay, then it's in particular integer if I take as right-hand side b a unit vector, okay? But what is the inverse of b times a unit vector? That is just the the ith unit vector. That is just going to be the ith column of the matrix, okay? So b to the minus 1 times the ith unit vector gives me just the ith column of this inverse matrix. So that means, by assumption, this X is an integer vector, and that means that all the columns of the inverse of this matrix B are going to be integer vectors. So therefore, also the determinant of this inverse is going to be an integer value. And now we know from linear algebra that the product of the determinant of a matrix B with the determinant of the inverse of that matrix, so these are just two inverses of each other, so the product is going to be 1. Okay, and now we argued that this is an integer value. Since B is an integer matrix, also the determinant of B is an integer value, so the product of two integers should be 1. That can only be the case if both are plus 1 or minus 1. So we have proved that the solution to such an equality system here is integer valued for any right-hand side B, if and only if this matrix B is indeed unimodular. And now we can move to the main theorem. So if we have our constraint matrix A and the right-hand side B, and we consider a polyhedron defined by these linear inequalities and non-negativity, and we get the following theorem. If this matrix is totally unimodular and B is integer, okay, then the corresponding polyhedron has integer vertices only. And the proof of that is now just a simple summary of everything that we did so far. Okay, so let's briefly have a look at it. So if the corresponding polyhedron is empty, there is nothing to prove. So let's assume it's non-empty. And we write this polyhedron P of A in the following way. So that is our inequality system, AX less or equal than B. And here on the bottom, we have the non-negativity constraints. So this is just a unit matrix. So since this matrix is totally unimodular, also this matrix is totally unimodular because we can just add unit vectors to it and it stays totally unimodular. Okay, so this constraint matrix, including the non-negativity constraints, is still totally unimodular. And now we consider any vertex of this polyhedron. Such a vertex must exist because we have a polyhedron with non-negativity constraints and that is pointed, hence it contains a vertex. So we know that any vertex V will be obtained by taking a subsystem of this linear system, and now I mean this linear system here, with equality, and we also know that the rank of this subsystem should be n, the dimension. That because we know that each vertex is defined by n linearly independent rows of the original system, and therefore we will have a rank n system in this subsystem A0. Okay, so the rank is n, and the matrix A0, the submatrix, is also totally unimodular because it was obtained from as a submatrix or a subsystem of this totally unimodular system. And remember that we can delete rows and columns from a total unimodular matrix. So this is not only totally unimodular, but it's also unimodular. Why is that? Because its determinant is non-zero, because it's a full rank system. Okay, so this A0 is a unimodular square matrix, so it has determinant plus or minus 1. And then we can use our previous theorem. So the solution to the corresponding system, if I write it down again, A0x equal to B0, that will have an integer solution, and that is exactly our vertex here. Okay, so this vertex must be an integer vertex. Now that proof is one half of the proof of a well-known theorem in polyhedral combinatorics by Hoffman and Kruskal. So we actually proved sufficiency. So we proved that if the matrix is totally unimodular and the right-hand side is integer, then the corresponding polyhedron has integer vertices only. And as a matter of fact, also the opposite is true. So if this polyhedron defined in this way has integer vertices for all integer right-hand sides, then the matrix is totally unimodular. So for a proof, see the lecture notes. I'm not going to do this proof in the lecture. I'm only making a little warning here. So it's essential to consider this inequality system here. For example, if I replace this AX equal to B here in the definition of the polyhedron, then this statement is false. This statement is no longer true. Okay, so the most important case anyhow for us is this implication. So if we have a totally unimodular matrix and an integer right-hand side, then we will get integer vertices only, and that's the interesting case for us. Now, which matrices are totally unimodular? And in order to make it a little bit more workable, there is another sufficient condition on total unimodularity, which is very handy, at least with respect to all kinds of problems that are defined on graphs. Okay, so if we have an integer matrix A having only 0, plus or minus 1 entries, then the following two conditions, these two conditions here, are sufficient conditions for total unimodularity of A. And let me try to explain that. So what I have to do is I have to be able to partition the rows of the matrix into subsets R1 and R2 such that the following is true. I mean, I have only at most 2 non-zeros in each column. And so that means in each column I have at most 2 entries. And I have if I have 2 entries in one column which have the same sign, so +1 or -1 then they must appear in different parts of this partition. And if I have a column with 2 non-zero entries of different sign, so +1 -1 for instance, then they can appear in either one of the 2 sides of the partition. Okay, so if these conditions are fulfilled, at most 2 non-zeros in each column, and then this partition property, then the matrix is totally unimodular. I think it's best explained on an example, which is an example matrix which is totally unimodular. So here we have at most 2 non-zeros in each column, right? So there is 2 non-zeros here, there is 1 non-zero here. If I have 2 non-zeros with the same sign, then they appear in different sides of the partition. So these are the partitions of the rows of the matrix. So this +1 and this +1 appear on different sides of this partition, and this -1 and this -1 as well. And if I have 2 non-zeros with different signs, then they can appear either here on this side of the partition or there on that side of the partition, but not distributed over the 2 partitions. Okay, and the singleton values actually don't matter. For a proof, it's not awfully difficult to prove, but I'm not going to do that here. You can do a proof, for example, by induction on the size of the square submatrices, or you have a look into the lecture notes. Okay, so that is a sufficient condition on total unimodularity, and you already see that if I talk about matrices with a +1 and a -1, that most probably will correspond to directed edges in a certain graph or in a network. And this is also a way how we can exploit this sufficient condition on total unimodularity. So the next part is going to be about integrality of solutions to linear programming problems. Now that we have done so much theory on polyhedra, polytopes, and integrality of vertices, it's time to harvest a little bit. So let's see what we can get out of all these nice concepts. So this is about integrality of solutions. So first observation is, if we talk about directed graphs, then as a matter of fact, the node edge incidence matrix A of any directed graph is totally unimodular. And as a proof, well, in the node edge incidence matrix of a graph, we exactly have one +1 and one -1 for each of the edges of the graph, right? So the tail and the head of the edge. So we can just use this previous sufficient condition on total unimodularity and choose all the vertices as one side of the partition and the empty set as the other side of the partition. So like in this example, right? So here we have the whole node edge incidence matrix of a digraph, and all the +1 and -1s are on one side of the partition, and we are done. So this fulfills the sufficient condition by Heller and Tompkins. And as a consequence, the node edge incidence matrix of a directed graph is always totally unimodular. So that is nice, because as a consequence, the linear program for minimum cost flow, that is something that we already knew, has integer optimal solutions whenever the capacities, which is the right-hand sides, and the balances, the other right-hand sides, are integers. Okay. And also, if we look at the dual of the corresponding linear program for minimum cost flow, the dual LP also has integer optimal solutions whenever the costs are integer costs. Okay. So we can recover quite easily our previous observation, namely that the primal dual algorithm actually always computed integer optimal solutions. And now we know what the reason for that is. That is because the node edge incidence matrix of directed graphs is a totally unimodular matrix. So the whole system is a TU system, and it always has integral vertices, which correspond to the integer valued flows. All right, so let's move on. What about matching, the matching problem? So here's the next theorem. The node edge incidence matrix of an undirected graph G is actually totally unimodular if and only if the graph is bipartite. This is maybe not so much of a surprise either. And let's briefly see why this is true. So if a graph is bipartite, we already are given the corresponding bipartition of the rows of the node edge incidence matrix, right? So if the graph is bipartite, we have a partition of the vertices of the graph in two sets, and all the edges go from one set to the other set. So that defines our bipartition of the rows of the node edge incidence matrix such that the +1s are always on different sides. Okay, so we can again use this sufficient condition for total unimodularity and can conclude that the corresponding node edge incidence matrix is totally unimodular if the graph is bipartite. But I claimed an if and only if, so I also should show that if the node edge incidence matrix of an undirected graph is totally unimodular, that then the graph must be bipartite. And how do we see that? Well, we just see that if the graph would contain an odd length cycle, then it would have a submatrix B which has a determinant which is not equal to 0 plus or minus 1. Hence, the matrix cannot be totally unimodular. Okay, so let's look at this argument, for example, at a cycle of length 3, but the same is true for cycles of length longer than 3 as well. So we have three vertices A, B, and C, and they form a cycle of length 3. And then this would give rise to the submatrix here on this paper. So for instance, edge number 1 here would be incident with A and B, edge number 2 here is incident with B and C, and so on. And if you compute the matrix, the determinant of the submatrix, you will see that this determinant is equal to 2. So hence it is not equal to plus or minus 1, and also not equal to 0. And hence, if a matrix, if the node edge incidence matrix is supposed to be totally unimodular, the graph cannot have any cycle of odd length. Okay, hence the graph is bipartite. All right, so let's see what this gives us. And let's write down the matching problem as an integer linear programming problem. Okay, so recall that delta of V is all the edges incident with a node V. And we use variables xe, which are equal to 1 if an edge is chosen to be in the matching and 0 otherwise. So we want to maximize the total set of edges that we select. So that would be a maximum size matching. The constraint is that at each node, I can only select at the most one incident edge, and the variables should be 0 or 1. So that's a integer linear programming formulation of the matching problem. And if I write down the same problem as an LP with using the node edge incidence matrix A, okay, so I would maximize 1 times x because all the edges have equal value, 1. The constraint is that A times x should be at most 1, so there's a vector of 1s on the right-hand side. And the constraints exactly say that all the edges incident with a node V, I can only select at most one of those, right? And the variables should be non-negative and integer. Notice that we don't have to explicitly write down that the variables should be at most 1, because this is implied by these constraints here. Okay, so what we know now is that in this formulation of the problem, we are interested in integer valued solutions, and we know that this constraint matrix A is totally unimodular if and only if the graph is bipartite. So what does this give us? Well, we can drop the integrality constraints for bipartite graphs. Okay, so if I just write down the corresponding linear programming problem, so that's the same problem that we had before, only with the integrality constraints dropped, right? So then this linear programming problem, for bipartite graphs at least, will have a constraint matrix which is totally unimodular. Hence, all the vertices will be integer valued, so will be integer vertices, and these integer solutions correspond to matchings. So the optimal solution, so the integer optimal solution, a matching, can just be computed by solving this linear programming problem without explicitly requiring that the variables should be integer valued. So that is true if the graph is bipartite. And we already know that this is not true if the graph is not bipartite, right? So we had this example already on the one of the first slides of the lecture. When we look at the same problem or the same linear programming formulation for this triangle, for instance, then we have already seen that there exists an optimal solution in which each of the edges is chosen with value 1/2. So that's a fractional value, and this gives us the only optimal solution value, which is 3/2, right? So in general, for non-bipartite graphs, the corresponding linear programming formulation doesn't give integer optimal solutions, but it does give us integer optimal solutions if the graph is actually bipartite. And why? Well, because the constraint matrix is totally unimodular. So that's kind of nice. So we could solve matching problems for bipartite graphs by just using a linear programming solver. But we can actually do a little bit more. So we can derive a very well-known and classical theorem in combinatorics. That is when I consider the corresponding dual of this linear programming formulation. Okay. So for bipartite graphs, the same is true also for the dual of this LP. Okay, so also the dual will have a constraint matrix which is totally unimodular, and hence the same statement is also true for the dual, so we always will have integer optimal solutions. But let's first understand what the dual of this LP actually is. Okay, not only for bipartite graphs, but just in general. And here let's look at the example. Here is a non-bipartite graph. Again, this little triangle. Here's again the formulation of the matching problem as a linear programming problem requiring also integrality. So in the matching problem, we select edges of the graph, right? 1, 2, and 3. So as, maximize the number of edges such that for each of the vertices, at most one edge is incident with it. In the dual to this problem, we will select vertices of the graph, so nodes of the graph. So we will select A, B, or C, or several of them. We select a minimum number of nodes of the graph with the constraint that for each of the edges of the graph, so for example, for edge number 1, we should select at least one of the two endpoints. Okay, so YA plus YC should be at least 1, just means that for this edge number 1, I should select either A or C or both. And that should be true for all the edges of the graph. So that's known as the so-called node cover problem. So it means I have to select a subset of the nodes of the graph. So for example, A and B, and now I have selected a subset of the nodes that cover all the edges of the graph. So all the edges of the graph are now incident with at least one of the nodes that I selected. Okay. So by weak duality, we know that in general, the size of a maximum matching, which is denoted by mu here, is at most the size of any node cover of the graph. That is just by weak duality, right? So the matching problem is the primal linear programming problem. So if you forget about these integrality constraints for a moment, we just have a primal linear programming problem, which is a maximization problem. This is the corresponding dual to this linear programming problem. And any solution value or any solution of the primal gives a value which is upper bounded by any solution value of any feasible solution of the dual. So that exactly means if I take as feasible solutions integral solutions, then I will get the statement that the size of any matching, so that's the solution value of a primal solution, is upper bounded by the size of any node cover, which is the solution value of any feasible dual solution. Now, the interesting thing happens if we consider this whole situation for bipartite graphs, where we actually know that for both problems, we can drop the integrality constraints because of the fact that the constraint matrix will be totally unimodular. And then we get a very well-known and classic theorem by Koenig, which says exactly that the size of a maximum matching in a bipartite graph equals the size of a minimum node cover in the graph. So here is a matching of size 6, and here is a node cover of size 6 as well. And since we know this is a primal dual pair, so this is the matching is a primal feasible solution, the node cover is a dual feasible solution, we know that on this example, these must be optimum solutions to the corresponding problems as well. But now, how do we prove Koenig's theorem in general, not just on this example? Well, you could write down a proof from basic principles, but we can as well just use the theory that we have developed so far. Because now the proof just follows from everything that we have derived so far. So the only thing that I have to realize is that the matching linear program and the node cover linear programming, these are the duals of each other. Moreover, for bipartite graphs, the corresponding constraint matrices are totally unimodular. So that means all the vertices of the corresponding polyhedron here have integer vertices, and all the vertices of the corresponding polyhedron here also have integer values. So it's integer vertices. And hence, because we have integer optimal solutions to both problems, primal and dual, we have an optimal primal dual pair, which is exactly Koenig's theorem. So once again, for a bipartite graph, the constraint matrix A is totally unimodular, so we have an optimal primal dual pair for these LPs that is integer, and this is the desired matching and node cover. And remember, this is not true for non-bipartite graphs. We have seen an example which is given by this triangle. Right, in the triangle, we can select at most one of the edges in the matching problem, and for the node cover problem, we will have to select two of the endpoints. So there we have a gap. All right, so this is already a little bit of the consequences of all the theory that we have developed. And now I want to give a glimpse on what do I do if I do not have total unimodularity. Okay, so what do I do if there is still a gap between the LPs and the corresponding integer linear programs? Okay, so we have seen two concrete examples of problems, minimum cost flow and the bipartite matching problem, where we could solve an integer linear program, a discrete optimization problem, by just reducing it to a linear programming problem. So we could find integer optimal solutions by just formulating this problem as an LP, as a linear programming problem. The question now is, what do we do if we do not talk about minimum cost flow and bipartite matching? Or more generally, what do we do if we have a constraint matrix which is not totally unimodular? Can we do something comparable to that? Can we still solve discrete optimization problems by linear programming techniques? And this section of the lecture is meant to show that this is in principle possible. Okay? So the object of interest is actually a discrete optimization problem, and discrete means that the variables are constrained to be integer valued. Okay, so we have a feasibility region described by these linear constraints and non-negativity constraints here, and the axis should be integer. And I claim that this problem, it's an integer linear programming problem, is in fact equivalent to another problem, which is a linear programming problem. So this is the same problem, same objective function value, only now the feasibility set is constrained to be something else. So now the axes are required to be of the set Pi, and what is that? Well, this Pi is the convex hull of all the integer feasible points. Okay, so I look at all the feasible points which are integer up here, and I take the convex hull of those. Okay, so this is in principle a linear programming problem. So this is going to be a polytope, and hence this is just an LP, which I could try to solve. And I claim that solving this LP is in fact equivalent to solving the above integer linear program. Well, in what sense is this equivalent? Well, when I solve this linear programming problem here, I know that the set of optimal solutions, that's going to be a face of this polytope here, okay? So optimal solutions of this LP are a face of this polytope Pi. Well, and then by definition, this face will contain an integer point. So by using something like the simplex algorithm, I will find an integer vertex, and that means I will find an integer optimal solution to this problem up here, okay? The big trouble, of course, is that I do not have an explicit description of this set Pi here, right? So that's the convex hull of all the feasible integer points. And in general, I do not have this description. And the best way to make that very explicit is by a picture, and that is actually the cover of the book by Lex Shriver on integer programming. So in our explicit description of the problem, we had constraints ax less or equal than b, and that would be actually correspond to this white inequalities here. And we have the explicit requirement that we are only interested in integer points, right? And so therefore we have feasible integer points here inside this white polyhedron, and that's the interesting objects. And what we would like to have is a description of the convex hull of the integer feasible points. So that would be this red object. So in general, this ax less or equal than b is not this explicit description, but we can get it. And that is the message of this last part of this lecture. So how do I get the explicit description of the feasible integer points here? And the idea is quite simple. So I start out with the original description of the problem. That would be the white polytope on the picture. And I'm interested in the convex hull of the integer points. So that would be the red polytope on the picture. So what do I do? Well, remember, this is just a set of linear inequalities which are valid for any feasible point. So I can take also a linear combination of these valid inequalities, and that will also be feasible, right? And that is what I do by multiplying the whole thing, or this vector lambda just denotes the corresponding fractions of all the m inequalities that I actually take. Okay, so when I have this formulation here, lambda transpose ax, that is just a linear combination of all the original inequalities that I have in my original description. And then I get a lambda transpose times b on the right-hand side, right? So if it happens that the coefficients here on the left-hand side are integers only, okay, so if this lambda transpose A is just integer values, I look at the right-hand side. So the right-hand side is lambda transpose times b. That is some number. And if this number happens to be a fractional number, I can round down the corresponding right-hand side and thereby obtain a stronger inequality, stronger than the one that I started with. And that's a so-called Schwarzschild-Montgomery cut. Okay, so I think it's easier explained on a very simple example here. I have two inequalities, x1 plus 2x2 smaller or equal than 4 and x1 smaller or equal than 1, both required to be non-negative and integer. Okay, so x is integer. Now if I take 1/2 of the first inequality plus 1/2 of the second inequality, what do I get? That corresponds to taking this lambda up here to be 1/2, 1/2. And then I get an inequality 1/2 times x1 plus x1, which gives me x1, 1/2 times 2x2 plus 0, which gives me x2. So I get x1 plus x2 on the left-hand side. So notice that the coefficients here are integer coefficients. And on the right-hand side, I get 4 plus 1 divided by 2, so 5/2. And now the important thing to realize is we are interested only in integer solution values, right? So this left-hand side must be integer. The right-hand side says 5/2. So x1 plus x2 must be smaller than 5/2, but this must be an integer value, so it cannot be larger than 2. Okay, so therefore I can round down this 5/2 to 2 and get this stronger inequality, which I have obtained by a linear combination of the two original constraints here, okay? And by rounding down the right-hand side. So I have the same example also in an illustration here. So this is my constraint that x1 should be at most 1. This is my original constraint, namely x1 plus 2x2 should be at most 4. Okay, so therefore, originally in the description of my problem, and everything should be non-negative, so the original description of the problem would give me this feasibility polytope. But since I'm only interested in integer points, I'm only interested in those points, this would be the inequality that I'm interested in. Then I would have obtained a description of all the integer points, all the feasible integer points by linear inequalities. And that is exactly the constraint that I get when I combine the two other constraints. Because this is exactly the constraint x1 plus x2 smaller or equal than 2. That is this constraint here, which I have obtained by combining the two original constraints, each with a fraction 1/2 and rounding down the right-hand side. So what this so-called Schwarzschild-Montgomery cut actually does is it cuts away this non-integer vertex of the original description. Okay, so let's see how we can do that a little bit more systematically. So this is the original description of the problem, ax less or equal than b and x integer. And we are interested in the convex hull of all the integer points. Okay, so the first thing is the linear relaxation. So that would be just dropping the integrality constraints. So that was on the previous picture, the earlier picture, the white polytope, right? Now, okay, and now we do the following. We add to this description all these Schwarzschild-Gomory cuts that I can obtain by combining the original constraints. Okay, so that is the so-called first Schwarzschild closure. So here I take all the vectors x, which I can obtain by linear combinations of all the original constraints and rounding down the right-hand sides. And I have to be a bit careful because I have to make sure that the coefficients here, so this lambda transpose A must be an integer vector. So lambda transpose A must be integer because only then I can be sure that I am allowed to round down the right-hand side, which is what I do here, okay? And here the lambdas are taken to be all the combinations. So that's just the kind of fractions with which I take the original constraints of the problem, okay? So there's a few observations that we can make about this. So what I'm doing here in this definition, I'm allowed to vary the lambdas. I'm essentially taking all possible lambdas here, okay? First observation, and that's a very nice exercise actually, is to see that this first Schwarzschild closure is actually a polyhedron again. So it is described by finitely many inequalities. That's not obvious because here in principle, I can use infinitely many values for lambda, for this vector lambda, right? But that's not necessary. All right, so it's a polyhedron. Next, it's a subset of the original linear relaxation. So this was the linear relaxation where we dropped the integrality constraints, and the first Schwarzschild closure is actually a subset of this. So that is quite simple to see because I can take as lambdas all the unit vectors, and that gives me exactly the original description. Okay, so all the original constraints are still there, and therefore it's only a more constrained set of points, and therefore it's going to be a subset of the linear relaxation. And by construction, it still contains all the integer points. Because if these coefficients, so if lambda transpose A is just an integer vector, I'm really allowed to round down the right-hand side because this is going to be an integer value, and hence I can round down the right-hand side to the next integer. Okay, so all the integer points are still contained in the first Schwarzschild closure. So indeed, I have the situation that the object of interest, Pi, is a subset of my first Schwarzschild closure, which is a subset of the linear relaxation P. So the only tricky thing in this definition of the first Schwarzschild closure is this part here. So which vectors lambda do I actually have to take? Because I have to make sure, in order to be able to round down on the right-hand side, I have to make sure that the corresponding coefficients on the left-hand side are integer coefficients. So lambda transpose times A should be integer, an integer vector. And as a matter of fact, there is only finitely many such lambdas that I need to consider, which at the end show that this is indeed a polyhedron. But as you can already imagine, if I call this the first Schwarzschild closure, there should also be a second one, and this is also true. So now I have done that, and I have obtained a new linear system, and I just do the same on this new linear system again, okay? So by iterating this construction, I get a sequence of polytopes. I started with a linear relaxation, then I just computed the first Schwarzschild closure, and this is again a polyhedral description, a description of a polytope by linear inequalities, and I can again do the same Schwarzschild rounding, and I get the second Schwarzschild closure, and so on and so on. And all these by construction will be supersets of the convex hull of the integer points. And there is a deep theorem by Schwartal and Gomery which says that, well, there exists some finite value k such that I actually have constructed the convex hull of the integer points. And that is exactly the description of the integer feasible points by its facets. So I iterate this procedure, first Schwartal closure, second Schwartal closure, and so on. And some pk, so some kth Schwartal closure will be equal to the convex hull of the integer points. And the Schwartal rank of a polyhedron or a polytope is the minimum k where this happens. And I'm not doing the proof. The proof is an inductive proof of the dimension of the polyhedron. And I have uploaded a part of a chapter of a book which contains this proof for those that are interested. On the previous little example, we had a situation that the addition of just one additional Schwartal-Gomery cut gave us the convex hull of the integer points. So if I just go back to this example that we had earlier, that was the example here. Just the addition of this one linear combination of the two inequalities that I have in the system gave me exactly the cut that resulted in the convex hull of all the integer points, right? So here the first Schwartal closure was already equal to the convex hull of the integer points. So here is again an illustration of that. The linear relaxation was this one here, and the facets of the integer points, right? That is this object here, defined by this additional inequality here, and the first Schwartal closure here is exactly equal to the convex hull of the integer points. So the whole set of facets of this convex hull of integer points would be this constraint x1 equal to 0, x2 equal to 0, x1 equal to 1, and then the one that we derived by Schwartal-Gomery rounding, x1 plus x2 equal to 2. So intuitively, what happens when I compute the first Schwartal closure is the following. I consider all supporting hyperplanes of the original description of P, and I move them towards the integer hull until they touch some integer point. So if you look down here in this example, for instance, the original inequalities were these two. I take a combination of these two inequalities, that would be this supporting hyperplane here, okay? And now the rounding procedure means that I can move this inequality a little bit further towards the integer points, and the rounding actually stops whenever I hit an integer point here. So I would be able to cut off this little piece of the original description here. And I do that for all the supporting hyperplanes of the original description, or of the original polytope. So why would I ever need more than the first Schwartal closure? And here is a simple example that shows that you actually in general need that. So we have a polytope or a description of a polytope here by three linear inequalities, this triangle here, which has a Schwartal rank larger than 1. So the first Schwartal closure does not yet give me the convex hull of all the integer points, which is just a square. And indeed, if you look at it, if I take a supporting hyperplane above here, so for example here I could be moving that into this direction, and I will be bound by integer points here, and the first Schwartal closure will be this object here, okay? So that would be corresponding to these constraints that I have obtained by Schwartal-Gomery rounding, but not more, okay? So the first Schwartal closure is not yet the convex hull of all the integer points. Only the second round of Schwartal rounding will give me actually the convex hull of integer points. Okay, so now what I would like to do is I would like to use this Schwarz-Montgomery procedure or Schwarz-Montgomery idea to a concrete combinatorial optimization problem, namely the matching problem. Okay, so let's first define the so-called matching polytope, which is just the convex hull of all the incidence vectors of matchings. Okay, so that's all the variable xe is equal to 1 if I select an edge, and I take the convex hull of all these vectors when x corresponds to a matching. And we know we can describe this by these linear inequalities here, ax less or equal than 1, where A is the node edge incidence matrix of the corresponding undirected graph. Okay, so that's the object of interest, the convex hull of all the integer solution values. Okay, convex hull of all the matchings. Now, if we drop the integrality constraints from this description here, we get the so-called fractional matching polytope, right? So if we drop the integrality condition on the variables, we get another polytope here, which fulfills these degree constraints, ax less or equal than 1. So at most one edge at every vertex, x non-negative, and notice that these constraints also enforce x to be at most 1. Okay, so that's the fractional matching polytope. And that would be, say, the natural description of the matching problem. And we know that if we want to have a real matching, we have to make sure that x should be integer valued. Now, the first observation, I mean, the question is now, how do these two objects exactly relate? Okay, and that's what I start to do with this first theorem. So we have the matching polytope here on the left. So that's all the integer solution values. And we have the fractional matching polytope here on the right. So that's all the solutions, including maybe also fractional solutions. And it's clear by definition that the convex hull of all the matchings, so all the feasible integer points, is that the subset of P here, which is all the solutions, including the fractional ones. But we have equality if and only if the graph is bipartite. So that is all, that is something that we know already. So let's just go through the sequence of arguments once more. So first of all, the integer hull is contained in the fractional matching polytope. That is trivial because this Pi is the convex hull of all matchings. But all the matchings are feasible points in this fractional polytope too. And this fractional matching polytope is also convex. But Pi is the smallest convex set containing all the matchings. So this is also a convex set containing all the matchings. So therefore, this containment is clear. And in the other direction, if I have a bipartite graph, I know that the vertices of this fractional matching polytope actually are integer vertices, right? And these integer vertices correspond to matchings. So therefore, they are also contained in this object on the left-hand side. Okay. So, but if all the vertices of P are contained in Pi, then P itself is also contained in Pi, right? Because P is equal to the convex hull of all its vertices. That was Minkowski's theorem, okay? So Pi is also a convex set. P is the convex hull of all the integer, of all the vertices, and these are integer vertices, and these are matchings themselves. Okay, so we have equality if and only if the graph is bipartite. About the only if, so that this is actually also a strict containment for non-bipartite graphs. We had an example of that already at least twice. So here is the example once more. So let's look at the matching polytope for non-bipartite graphs. And here is again the graph or the example, which consists of a triangle graph. So three vertices all connected by edges. And then the corresponding matching polytope would be the convex hull of all the matchings. So that would be none of the edges and then either of the three edges. So that would be this object here. So the convex hull of these four vertices here. So that would be the matching polytope. And the polytope associated, the fractional matching polytope, that is also something that we had earlier, would be this one, which also contains this non-integral vertex 1/2, 1/2, 1/2. So we indeed see that in general, so for non-bipartite graphs, the matching polytope is strictly contained, a strictly subset of the fractional matching polytope. And now we are wondering, okay, so we have seen this Schwarzschild-Montgomery rounding procedure. Can we actually get from this description that description by using Schwarzschild-Montgomery rounding cuts? And exactly this is true, and I will show you how. So I start by writing down the description of the matching problem. So we have two sets of constraints here. That is the degree constraints, right? Saying that I can select at most one edge incident with any vertex V. And we have the non-negativity constraints. So X should be non-negative. Now, in the Schwarzschild-Montgomery cuts that I'm going to add, I'm going to show you how to derive or define some of the Schwarzschild-Montgomery cuts. I'm taking a combination of these two constraints. Okay, and I do that in the following way. I consider any subset of the vertices S, and I take the corresponding degree constraints here with a weight 1/2. Okay, and all the other degree constraints with a weight 0, so they are not taken into account. So only the degree constraints for the vertices in S. Okay, and then with a weight 1/2. And then I also take some of the non-negativity constraints here. Namely, I take 1/2 of these non-negativity constraints for all the edges that are in the cut induced by S. So that is going to be a linear combination of some of the original constraints in the description of the problem. Okay, so let us write down what we have. So we have this factor of 1/2 everywhere. We have all the vertices in S and all the edges incident with the vertex in S. And we subtract all the edges in the cut induced by the set of vertices S. On what do we have on the right-hand side? Well, on the right-hand side, the right-hand sides of these degree constraints are 1, and the right-hand sides of the non-negativity constraints are 0. So therefore, on the right-hand side, we get the cardinality of the set S and this factor 1/2 that we have chosen. All right. So far nothing really interesting happened, but let us look what this sum here actually is. So here I'm actually counting all the edges which completely lie inside S double once from both endpoints. Okay. The edges that lie in the cut also appear in the sum here, but only once. So the edges in the cut have one endpoint inside S, and from that endpoint we are counting once the corresponding edge. And this corresponding edge is subtracted here again. So the edges in the cut disappear. And then I have twice the edges which completely lie inside the set S. So therefore, what remains is just all the edges which completely lie inside S. And on the right-hand side, I have 1/2 times the cardinality of that set S. So far I have just made a linear combination of some of the valid inequalities of the original problem, right? Now I can round. So the rounding consists of rounding down whenever the set has an odd number of nodes, right? So for example, if that is 7 nodes, then that would be 3.5. I would round down this right-hand side to 3. And that gives me the so-called odd set inequalities. So after rounding down the right-hand side, the corresponding Schwarzschild-Montgomery cut that I just explained look like this, right? So having round, so if this is an odd set of vertices, so like 7 here, that would be 6 divided by 2. So then the right-hand side would be 3. Okay, and that is the corresponding odd set inequality. And it expresses the intuitive fact that if I have an odd set of nodes here, right? So here that would be 1, 2, 3, 4, 5, 6, 7 nodes. I can only have 3 matching edges inside this set S. Okay, so that's certainly a valid inequality, and that's an inequality that we didn't have before in the original description, right? And here comes the theorem. So the actual matching polytope, the convex hull of all the actual matchings, equals the following polytope Q here, and here I just have the linear description that I had before, x is non-negative, and I have just added these odd set inequalities that we just derived. So that's just some of the Schwarz-Montgomery cuts that I have added to the linear description. And the theorem says that these two polytopes are equal. So adding these very specific Schwarz-Montgomery cuts is already sufficient for obtaining the convex hull of the integer points. Okay, so in particular, the convex hull of the integer points is equal to the first Schwarz-Hull closure for the matching problem. I'm not going through the proof here in this lecture. I'm just giving this as a theorem, and I want to illustrate that by using our previous example. So what would be the corresponding odd set inequality that we have to add in order to get from the fractional matching polytope the actual description of the convex hull of all the matchings? And that is exactly, the underlying graph was an odd set itself. So that would be exactly the odd set inequality that I get for this odd set of the three nodes of the graph, which would be, the odd set inequality x1 plus x2 plus x3 being at most 1, because among the three edges, right? If I pick the three vertices, the three nodes of the graph, I can have at most one matching edge. That's exactly the Schwarz-Montgomery odd set inequality or Schwarz-Montgomery rounding cut. So indeed, by just adding on this small example, this one odd set inequality, I cut away this fractional vertex and I obtain exactly the matching polytope, so the convex hull of all the matchings. And this works not only for this small example, it just also works in general, and that is what this theorem here says. So that now means we also know how we could solve the matching problem in non-bipartite graphs by using linear programming techniques. Namely, what I have to do is I have to add odd set inequalities. This does not, unfortunately, give a description of the problem which is compact, because there could be a very large number of odd set inequalities that I might have to add, right, for all the odd subsets of the vertices. So per se, this doesn't give a efficient procedure for solving combinatorial optimization problems, but it gives rise to another idea. So I do not have to add all these Schwarz-Montgomery cuts. There's also other classes of cuts. I do not have to add all of them. Maybe it suffices to add some of these cuts and see if I already get an optimal solution. And that is known as so-called cutting plane algorithms. So either I get an optimal solution or I can add even more cuts later on. Okay, so if I want to solve an integer linear programming problem, I first consider the corresponding linear relaxation, and I can compute, for example, using the simplex algorithm, an optimal solution to that. Now, since I require the solutions to be integer, if I already get an integer solution by solving this linear relaxation, then I'm done. And this will, for instance, be happening if I consider problems which are described by totally unimodular systems, right? So a minimum cost flow or bipartite matching. Otherwise, I will get an optimal solution, probably, which contains still some fractional values, x. And then I can do the following. So as long as I still find optimal solutions x star of the corresponding linear relaxation, which are not yet integer, I try to solve the corresponding separation problem. And that essentially means I can try to find, for example, a Schwarz-Montgomery cut, which is a valid inequality for the integer points, but which cuts away the corresponding fractional point that I currently have. Okay, so I separate the current fractional optimal solution from the integer hull, and that could be, for example, by adding Schwarz-Montgomery cuts. Okay, so I add this new cut that I have defined or that I have found to the linear description that I started with, and I just resolve. If I get an integer solution, I am happy. I will have found an optimal solution to the original problem. If I still get fractional values, I still find even more cuts that separate these fractional values from the integer hull. Okay, and that is known as cutting plane algorithms, and this technique can be justified by the Schwarzschild-Gomory theorem. So at least theoretically, we can add Schwarzschild-Gomory cuts, and this procedure will terminate at some point in time. Okay, and as a matter of fact, this is also what is happening in actual solvers, in actual software for solving integer linear programs like Gurobi or Cplex. So adding strong cutting planes or finding the right cutting planes, that is one of the engineering art that is the core of all of these solvers for integer linear programs. So that is known as the cutting plane idea. I cut away fractional solutions until I happen to find an integer solution. So just once more, so if I optimize in some direction, I might not have to add all the Schwarzschild-Gomory cuts, but I probably can do the job with only adding some of the cuts which lie in the direction in which I'm actually optimizing. And hence this procedure could terminate much, much earlier than having to add all the, for example, Schwarzschild-Gomory cuts or other cuts that have been defined in the literature. Okay. All right, so that is a kind of outlook or a remark. And the next lecture is going to be about the question, well, what do we do with problems for which we cannot get, or most probably cannot get, polynomial time algorithms, and how are these problems actually defined or identified? Okay, so that's a mild introduction into computational complexity, including in particular P, NP, co-NP, and the most powerful tool in complexity theory, the idea of problem reductions. Thank you very much.